Okay, so since now we have a basic understanding about the topics that we learned so far, we are good to go with what's called as a configuration space. Now, consider a mechanical system with consider a mechanical system with n particles whose position vectors are given by say r vector 1 dot 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 r vector n, and their corresponding coordinates, their corresponding coordinates to each of them corresponds to x1, y1, z1, right? Because it's a vector, and this will represent dot 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 xn, yn, and zn. Now, where I want to define the DOF to be equal to the degree of freedom for such kind of system is denoted by small n, alright, which is equal to, see, there are 3, 1, 2, 3. There are 3 variables that describe for one system, and there are 3 other variables describe for n system. See this one, right? So that means I will have 3n degree of freedom. So how to interpret this? So you can say there are n. So there are capital N degree of freedom in x, capital N degree of freedom in y, and capital N degree of freedom in z, right? So what I'm going to do is I'm going to relabel the coordinate notations. Why? You will see it in a second. Why? I'm going to relabel the coordinate notation. So what I'll do is I'll say my u1 describe my x1, similarly my u2 describe my y, and my u3 describe my z, say y1 and z1. Similarly, my u4 will now denote x2, so on, such that my un denote my z small n, alright, it's small n. So what I did, I just relabeled the notation, and this is one of the smartest way that one can relabel the notation. And this is n tuplet, that means they are n tuples, and these are mathematical terms that have been used over here. They are n tuple small n. So now, by the word configuration, by this word, what do I mean by this word? So what I really mean is that if I know the location, I want you to listen very carefully. If I know the location of each one of those particles, then of course I know the configurations of the system, right? And the entire information of this configuration is included in this n tuple, right? Take a moment, pause the video, and take a moment to sink this information in your head. So I'll write it down if you want. See, what do I mean by configuration? What do I mean by configuration? If I know, so if I know the location of each one those particles, then of course I know the configuration of the system, right? So my entire information, okay, write it here. So my entire information of this configuration is included in the now, so instead of thinking, now one of the smartest ways that one can do is, instead of thinking the motion of n particle, the motion of n particles, say these are my n particles and it has some motion. So instead of thinking the motion of capital N number of particles, right, in 3 dimension, this is such a in 3 dimension, alright, in 3 dimension, I'm giving you the imaginative kind of a diagrammatic view of what I'm saying. Now I'm going to think of n particles, small n, I know this is a wrong diagrammatic view, but this is how I can interpret, I can make you understand this, in which the 3n dimensional space, let me repeat what I just said. So instead of thinking the motion of capital N particles, right, in 3 dimension, now I'm going to think the n, this n, think in n which is 3n dimensional space, which is instead of thinking, I mean, now I'm going, okay, let me restate the statement again. So instead of thinking the motion of capital N particles in 3 dimension, like I mentioned over here, now I'm going to think in small n terms. That means I'm going to think in which is in 3 dimensions, in 3 capital N, 3n, this n dimensional space. So I can define mathematically a space is defined by this, in which my u1, un are the elements of this particular space, this particular set, where the condition is ui should belong to the set, and this is my configuration space. Now, so as we know what we do in classical mechanics, we try to find the trajectory, and what we do in mechanics, classical mechanics is an unambiguous term, as I just stated it. Okay, so what we do in mechanics, we find the trajectory of the particle. So what is the view of the trajectory in terms of configuration space? So the trajectory in configuration space, I just read CS. In configuration space is given by ut, u1t, u2. You see, there is a time dependence coming into picture. This gives me the trajectory in the configuration space. Now I want you to note one thing. The trajectory, I want you to note, this is very important note. See, the trajectory of the system. A system may have any trajectory. Suppose this is my trajectory initially, or say this is my trajectory. Can be anything. This is my trajectory. The trajectory of the system in configuration space CS okay, just a second. I'm sorry. Yeah, the trajectory on the system of the system in configuration space and the trajectory of the particle in physical space are quite different. A point in a configuration space represents the configurations of the system. It's very important. A point in the configuration space, see this is my configuration space. A point in the configuration space represents the configurations of the system. What do I mean by that? I mean a single point there would represent the information about all the particles in the real space. This is exactly what I mean. See, a single point denotes in configuration space denotes the entire configurations of the system. So what does it mean in the light of the physical space or the real space? A physical point there would represent the information about all the particle in a Euclidean space or the real space. Thus, we have this kind of so the trajectory in a configuration space is given by this term. Let me write it down. Trajectory of the system this is the configuration space, or what we call as the C trajectory or the path. Now the trajectories of the particles happens in the real physical space. So now here the motion does not necessarily mean the equation of curve in the configuration space. An example would help you, right? Let's see. Suppose I have u1, u2 corresponds to 0, 0. Alright, this to u1, u2 till it's 1, 1. Now u1 of t and u2 of t is denoted by this font. So if you just see, this corresponds to a uniform motion, right? There is no hindrance over here. The u1, u2 is initially at rest, then after some time u1, u2 is at 1, 1, and u1 of t and u2 of t is nothing but the time element. Now this is a uniform motion. This is motion. So the equation of the curve is given by, let me write it. u1 is equal to u2 and u1 of t is equal to u2 of t would be t square. What just happened? I mean, here we have u1 of ut. It's a linear in time, thus it's a uniform motion. See, initially you have u1, u2 at 0, 0, and u1 of u2 would be 1, 1, and u1 of t and u2 of t is equal to t. This is linear in time. Thus we had the resultant motion was a uniform motion. But now, if I set the equation of curve to be u1 is equal to u2, so that my u1 of t is equal to u2 of t is the square element of the time, my equation of curve will remain u1 is equal to u2, but the equation of the curve, these two are not the same motion. Alright, one is uniform. Now this is non-uniform motion because it is not linear in time. This is let me write it down. This is non-uniform motion, and the reason being not linear in time. So these two motions not same, they are not same. One is accelerated, the second one, and other is the uniform motion, the first one. Other is uniform motion. So what does it tell us? An important information that we can devise from this example is the equation of curve in configuration space is not the trajectory of the particle. Trajectory necessarily has a time element in it. So let me write it down. Trajectory. So from this we can say the equation of curve in configuration space is not the trajectory of the particle. It's not necessarily the trajectory of the particle, because trajectory necessarily has a time element, and which is true. See, what we do is, even in mechanics, we say the particle is initially at this say x1, t1, and later on it goes through some other particle, other location, which say at a distance x2, t2 at some time t2. So the trajectory needs to take, in order for me to find the trajectory of the particle, we need to let the time evolve. We can keep the system. Oh, that becomes a complicated example, but just stick to it. So we necessarily need a time element. Now there is another space called the state space. I don't think you would require that, but it's but still it's important for our ongoing discussion. The state space. What does it mean? So rather than, I'll just write down the formulas for you. What are the spaces represent mathematically. Now, what we had initially was just u1, u2. Initially, we defined our configuration space in this order. These are the elements, right? We just had the positions. Say we just relabeled the coordinate system, and we got this. Now, what I will have instead is u1, u2, u small n, and I'll also have, because it's a it's a 2n dimensional space. It's not n dimensional space to contain only one element. If there is a 2n element, this implies there will be two elements. The element being, this is one element, and other, which is surprisingly is the velocity. Dot 1 dot y dot n, where I'll give the condition for each of them slash ui belongs to r and u dot I belongs to r. and mathematically I just described a state space. Now look, I want you to understand very carefully. Please listen to it. A curve in a state space actually gives you a motion. How surprising it is from what we just learned from the configuration space. A curve in state space actually gives you a motion. So different curves in state space would correspond, this is just a symbol, would correspond to different motion. Right? That's amazing. So, right, that's about the state space. Now you saw, okay, that is its position. Okay, I just want to represent this to be the state of the system. This is the state of the system. Alright. Now you are like, okay, fine, that's great, Karthik. You have u1, okay, that describes the position. You have u dot, okay, that's like a velocity. Then I can have u double dot. So you might be wondering, why not x double dot? Just say x double dot, or say acceleration in that case. Right? So can we do this? I'm really sorry to disappoint your research paperwork, because you might be thinking, yeah, I'm going to put a research paperwork by extending this to an acceleration principle, but the answer is no. You cannot do it. Let me tell you why. In Newtonian mechanics, the accelerations are not free variables, because see, you do know F is equal to ma. The acceleration is not a free variable. The forces in the system, they actually accelerate, they actually predetermine, not accelerate, I'm sorry, the forces in the system, they actually predetermine x double dot. I mean, what do I mean by it? Let me explain that also. I have force, alright? I have force. So I know for this kind of force, and for this particular force, and for this particular mass, my acceleration would be this. It has to be a definite quantity. I mean, if I know force and if I know mass, I can predetermine what my acceleration is. Thus, so there is no freedom in choosing. My freedom for choosing a variable so that I can apply it to a space as a general is not there. As a result, we cannot determine a space with acceleration as one of the state of the system. So that's about state space and configuration space. So in the next lecture, I'll try to explain what are called as the generalized coordinates. It's going to be very important for our further discussion on Lagrangian mechanics.